Hello, hello, everybody, and welcome to the Saturday edition of Advent of Code in Kotlin. Hope you're doing well. Hope you had a lovely Friday and lovely Saturday so far. I am still slightly regenerating after our Christmas party yesterday, but of course that didn't stop me from doing today's challenge. How's everybody doing today? If you're in the chat, if you've decided it's a good time to tune in, make sure you say hello. A couple of people I can see are already doing that. And as usual, I would be interested. How did you feel about today's challenge? How did it go? Were you maybe misled by something? Did you find a particularly clever solution or something like that? Who knows? I am enjoying some Christmas-themed tea today, in case anyone's interested. This is also a cup from one of the conferences from way back in the day. It's a Kotliners 2020 cup. I actually realized that I said in one of the first streams that I was going to show off all the cups that I was going to drink out of, but that kind of fell by the wayside. So now we're focusing on the important things, which is the hat, while we do the dramatic reading. See here. Congratulations. We have someone who got onto the global leaderboard. And I'm assuming by the avatar that's Ephemiant, who we had on stream a couple of days ago. So awesome. Congratulations for that. Julian says it was surprisingly easy for a Saturday. Herbert says, like yesterday, it looked harder on first glance than it actually was, and we will see what it looks like in just a little bit. And overall, it seems that the general assessment or the general opinion is a lot easier than expected. Surprisingly short and satisfying, which is nice. Johnny says they wrote a lot of code. Then they saw all the genius solutions on the Kotlin Slack and how to do it much easier. So we'll see. Maybe we'll see one of those today as well. Messed up and missed parsing negative numbers. It happens. We learn from these kind of experiences. I'll let you in on a secret. But I implemented my thing. I was also very much squinting at it, and after about 3 minutes, realized that I had switched a minus for a plus. So it happens to all of us. But yeah. Wonderful. Well, just like in the previous days, I am, of course, not alone for our Advent of Code challenge of the day. Like every day, we bring someone else on who brings a unique view on the problem, and today is no different. So I am very, very excited to introduce all of you to actually a repeat guest, not from this year, but from last year, and that is Olaf. Hi, Olaf. Welcome to the show.
Hi, Sebastian. Hi, folks. Thanks for having me.
Yeah, how are you doing?
I'm doing great. Yes. Today's puzzle had a part of that.
Yeah?
Yeah. It was surprisingly easy, as some said, for a weekend. We already had the discussion in our little group. And yes, given that the year was starting with some quite hard puzzles, comparatively hard for days 1, 2, and such, I think this was a treat for a weekend that I didn't expect.
Yeah, I mean, no one knows what Eric has in store for us. The pattern of oscillation between hard and easy. I'm not sure if it still holds or if it has a couple of bumps. If it will self-correct eventually.
Yes.
But yeah, I think it's very much as other people have said. It was a slightly easier time this time around. So yeah, it's not your first time joining us. I do remember that last year you wowed a lot of people. Also with your visualizations, not only with your solutions. That was a good time.
Yeah. This year so far, I must say, I'm waiting for the first great puzzle to visualize, like a maze or something that I can show what happens. I like those kind of puzzles. And well, so far I say well, there are some cool visualizations on Reddit if you watch these mega threads. But the kind of visualizations I like, as you might remember, is like these blocky kind of things where it looks like a little bit of 80s touch, whatever. So I don't do these graphs. So like a few days ago, you could have done this graph. You could have used GraphViz to graph the network. I think it was yesterday, right? Yes. But this is nothing I could do with my pixel game engine because it's just too pixelated for stuff like that.
Yeah, but I do remember this, and this is also what I love telling other people about. Is that you took this, essentially, I think it was a header-only C library, and you kind of ported that one for the purpose of doing these kind of visualizations?
Correct, yes. It's still there, and it's waiting for its first use case this year. Hopefully it comes soon.
Well, I'm hoping. I mean, if something will come before the 12th day, then of course we'll be happy to show off any visualizations that you've done on stream as well. And this is, of course, also a little call out to anyone else. If you are doing visualizations or you have anything else that you think would look great on stream, give me a shout. Like, post something in our Advent of Code Slack group, and we'll see if we can include it. And this is, of course, also just a brief reminder that we do have an Advent of Code community. So if you'll go to the blog post and you haven't joined yet, you can take a look at the community section. We have our Slack channel where people discuss, help each other, or just hang out and have a good time. And of course, this is also a great time to once again remind you folks that we have a whole campaign running around this, where you can win a couple of prizes. You can try to be fast and compete for the leaderboard, but also just being part of the leaderboard overall enters you to get the chance to win some prizes for Advent of Code in Kotlin. We've gotten feedback that the leaderboards that we had so far actually already all filled up. So we now have a 7th leaderboard. So if you're not yet in a leaderboard, you can go to leaderboard, then go to private leaderboard and hit copy paste the snippet for leaderboard 7 in here and click join. And then that will show up, I believe, all the way at the bottom here. So you'll see that leaderboard and you can compare with other people if you'd like to. Of course, we also have a bunch of other resources, including previous streams, including a previous stream featuring Olaf. So if you are still thirsting for a little bit more content in that direction, make sure you take a look at that later. Awesome. Great. Well, I think it's pretty much already time for us to kind of start discussing today's puzzle. Before we dive in, do you have any, like, when you came to this day, you were expecting something harder potentially for a weekend? Yeah,
definitely. So depending on how elaborate you write this code, I mean, this puzzle, the beauty of it is you can do as prescribed. So this is a kind of puzzle where if you just do what the algorithm that is explained wants you to do, you will find the solution. There is no trick. You don't have to optimize to avoid overflows or long runtime. So, and given these constraints, I'd say it was an easy puzzle for a Saturday. It could have very well made us do some optimizations to even reach to the result. Yeah. So like a few days ago, if you didn't think about it, you had like runtime of hours or days if you didn't think about the solution properly. Yeah. And so I would generally say these puzzles have exactly these two categories: the ones that just go straight forward and the ones that break your neck if you do that. And usually I'm always like, when you do part 1 and you know, okay, that went really smooth, you are really excited, like part 2 opens and you say like, okay, now I'm lost because I can't use my solution for part 1 here, or I try it and it doesn't work. And today I think was not that kind of a puzzle.
Yeah. Funnily enough, I mean, this we've mentioned on one of the previous streams. I believe it was the puzzle with the maps, with the like soil to location maps and so on. This actually hit the exact sweet spot where you could brute force the solution, but it would run for like a minute or so.
This was a very funny day. I mean, we can talk about that just for one word. I did the brute force thing because it was ready already. I started it, and I soon realized after 10 seconds, okay, this is going to take too long. Yeah, and then I started to optimize my code, and I was so lucky that I did not stop my process in IntelliJ. So it went on running while I was coding for a better solution, for an optimized, not brute force solution. And by the time I was done coding that, I couldn't believe my eyes. I saw the solution popped up in my run window. So usually when I see this happening, I'm always canceling my process because I know it will take for days. And this time, my first brute force solution, I think it took 8 minutes, something like that, something in the 8 minutes realm. Yeah. And exactly the time it took me to write a better solution. Actually, the better solution I wrote that morning was not the correct solution that does it in milliseconds, because you would have to look at the intervals and do the interval math. Where does it map to? So there is yet another really cool optimization for that day. And if you're interested in that, if you do it from the bottom to the top, like in reverse, I cut down my time from 8 minutes to 20 seconds. And it is still kind of brute force.
Oh, that's a clever one. Yeah, for that, I estimated roughly that, I did some back of the envelope math, and I quickly realized, well, this seems semi-feasible. It's still going to take a while, though. So I slapped a little bit of coroutines on it, which on my processor makes the whole thing go about 12 times as fast if I manage to parallelize it properly.
Yes.
And that made it, like you said, like my solution ended up running for maybe a minute or so. But then, I figured it's not good enough. We need to do a little bit more. So let's see if we'll encounter a similar situation in today's day 9, Mirage Maintenance. You ride the camel through the sandstorm and stop where the ghost's maps told you to stop. The sandstorm subsequently subsides, somehow seeing you standing at an oasis. The camel goes to get some water and you stretch your neck. As you look up, you discover what must be yet another giant floating island. This one made of metal. That must be where the parts to fix the sand machines come from. There's even a hang glider partially buried in the sand here. Once the sun rises and it heats up the sand, you might be able to use the glider and the hot air to get all the way up to the metal island. While you wait for the sun to rise, you admire the oasis hidden here in the middle of Desert Island. It must have a delicate ecosystem. You might as well take some ecological readings while you wait. Maybe you can report any environmental instabilities you find to someone so the oasis can be around for the next sandstorm-worn traveler. You pull out your handy oasis and sand instability sensor. That spells oasis. And analyze your surroundings. The oasis produces a report of many values and how they are changing over time, your puzzle input. Each line in the report contains the history of a single value. For example, 0, 3, 6, 9, 12, 15, or 1, 3, 6, 10, 15, 21, 10, 13, 16, 21, 30, 45. To best protect the oasis, your environmental report should include a prediction of the next value in each history. To do this, start by making a new sequence from the difference at each step of your history. If that sequence is not all zeros, repeat this process using the sequence you just generated as the input sequence. Once all of the values in your latest sequence are zeros, you can extrapolate what the next value of the original history should be. In the above dataset, the first history is 0, 3, 6, 9, 12, 15. Because the values increase by 3 each step, the first sequence of differences that you would generate will be 3, 3, 3, 3, 3. Note that this sequence has one fewer value than the input sequence, because at each step, it considers 2 numbers from the input. Since these values aren't all 0, repeat this process. The values differ by 0 at each step, so the next sequence is 0, 0, 0, 0. This means you have enough information to extrapolate the history. Visually, these sequences can be arranged like this. To extrapolate, start by adding a new 0 to the end of your list of zeros. Because the zeros represent differences between the two values above them, this also means there is now a placeholder in every sequence above it. So now in our triangle-like shape, we have a 0 at the bottom and then A and B placeholders above. You can then start filling in placeholders from the bottom up. A needs to be the result of increasing 3, the value of to its left, by 0, the value below it. That means A must be 3. Finally, you can fill in B, which needs to be the result of increasing 15, the value to its left, by 3, the value below it, or 18. So the next value of the first history is 18. Finding all 0 differences for the second history requires an additional sequence. Then, following the same process as before, work out the next value in each sequence from the bottom up, in this case getting us 0, 1, 7, and 28. So the next value of the second history is 28. The third history requires even more sequences, but its next value can be found the same way, filling in first the 0, then the 2, 8, 23, and 68. So the next value of the third history is 68. If you find the next value for each history in this example and add them together, you get 114. Analyze EuroAce's report and extrapolate the next value for each history. What is the sum of these extrapolated values? All right. Now, Olaf, you already mentioned in the beginning that you can approach this exactly the same way that the algorithm suggests, right?
Yes.
So I'm curious, when you started, like when you looked at this problem, was this also the way that you took, like first?
Pretty much, yes. I was pretty much in writing the code to produce each subsequent line. Yeah, so just like he described it in the very beginning. So the framework I'm almost always using these days is like most of the puzzles have a multiple inputs that you have to process and build a sum or a product or anything like that. So what I'm usually doing is I write this summing as a core of my part solver, and the internals, like what to do with one input, that usually starts like, okay, what do I have to do first? First, I have to build these lines that he prescribed. That's basically how I started.
Okay.
Yeah. But the way I'm thinking is always functional. So we might come to the differences of our solutions, as you've told me in the beginning, by just comparing what you could do. Yeah. So I can't help myself, but I'm always thinking functional.
I think it's a good instinct to have, and it's something that I'm still kind of working towards at some points, because man, once you've done it for a long time, sprinkling in a little bit of mutability here and there, it's just a little tempting, unfortunately. Yeah, we can also take a quick look at just the rough size of the inputs. So we have semi-big numbers, but per line we don't have that many elements. Like these lines aren't going entirely crazy. So since I think you poured a lot more thought into this than I potentially have, we're just going to start out by looking at my solution as the naive thing. The straightforward thing, the thing maybe that you find in your own code, and then we'll see how we can gradually improve this, both from turning it into functional, maybe also make it more performant. We'll see how that goes. So let me just open this up here. So the approach that I took was pretty much exactly like Olaf said, like as prescribed. You first just have to parse the input somehow. This is a story as old as time at this point, which is grabbing our lines and then ripping apart the individual numbers and turning those into integers so that we can work with them. So for each line, we get a list of integers. Because we are supposed to have the sum of all of those, our end result is just going to be the sum of whatever our predictions are for each line. And each line then just takes all those numbers. If I scroll down a little bit, I can actually fit the entire solution here quite nicely, and it does exactly as the algorithm is prescribed. I do all of this using mutable data structures, but of course, you could do this also using immutable data structures and copying, or do an entirely different approach. I just start off by saying, okay, at the end, I will have a list of integers, right? Because every line, or like every layer, so to say, is a list of integers, and I have multiple layers. So I'll just start off with a mutable list of whatever my input list was, also turned into a mutable list so that I can add elements. And then we just loop. And the condition for our loop is we want to continuously create these new lists until the line that we have just created is all zeros. So that's expressed just by using like the all predicate. Creating those actual lists is pretty trivial, because you'll just say, okay, I'll take a look at the last one that I've created so far, and then I'll use the windowed function, which gives you pairs. If you have a size 2, it'll give you pairs. If you have higher values, it'll give you a window of that size, and that's a sliding window. So it'll always consider the first number and the second number, and then the second number and the third number, like with overlaps. That's different from the chunked function that we've seen in some of the previous talks. Yeah, and the entire thing computing all of this is just doing b minus a. That's getting the differences, so you have an idea of how the value changes over time. And once you've done that, once everything is zeros, you can do as prescribed, and you can start filling in the placeholders. So you'll start not in the lowest layer, but in like one layer above, because the lowest layer is already all zeros. And here you will fill in the last value that is left of it. You'll take the last layer from, you'll take the last value from the list that is below it, and then you just concatenate this, so you add it to the end of your list, and you do that until you've added a prediction for each layer, and then the end result is the last thing that you've added. That is your solution in the very end. And that's pretty much it. It's the exact solution as prescribed. Yes, Johnny points out here that since we are iterating backwards, I am using down to, which gives me a reverse iterator. So going, instead of going up a bunch of values, I can give it a pretty big number, in this case my last index, and I'll go down to the 0th element.
May I ask a question there?
Of course.
So, when I see all of those -1s and +1s, that's what scares me off, and that's why I went to the functional side of the world. Yes. I'm always scared. Did you stumble across one of those +-1 things as a problem during today or maybe another day?
I actually, that's a good question. So today I certainly didn't. Now I'm trying to remember if I did on one of the previous days. I do recall having an off by 1 at some point, but that was during the working with the ranges. Because when you have ranges, it's always like you have an offset and then you have a length, and then but you might want to actually just consider the last index, which those are off by 1 classically. So you might have to do some tuning there. I don't know if functional programming would have helped me in that scenario. Made it nicer.
Let's see. I don't know. Certainly, I always have my one-off errors when I try to do these direct accesses to some indices. That's always a nice way to screw up the morning.
Oh, 100%. I agree. If there is a nicer way, I'm very excited to hear about it. And also, Alexander also mentions that, well, we do want to discard the last index, but obviously... we could just change this a little bit, but he suggests saying we could do layers.indices. That's a range, and then reverse that one. It still wouldn't, like, we would still have to somehow get rid of that last layer. So you would still do a drop. I'm not sure if that makes it particularly nicer, but it's probably more expressive than using down to. I'll actually give you that. So that's a pretty good point. Andreas already comes out here with the small spoiler. I have no -1 in my functional solution, so it's definitely possible. So why don't we actually just head over, and I'll move over to the Code With Me instance of IntelliJ that I have open here, and I'll follow you, Olaf. So Olaf is just connected to my machine. The repository is checked out on my machine, but Olaf can, of course, still control things here. And then I'll let you walk us through your solution.
I just saw that the collapsing doesn't work, but I think you had that on the stream already. So I'm just moving away part 2 by adding blank lines here.
Fine. Very good.
Okay, cool. Yes, I just looked at my code and there is no -1 for sure here as well. So yes, I can agree to that last comment. Yeah. So basically, just to get you into my solutions, there is a little framework class I use, so you don't see my read lines here, but it's very easy to understand. The input here I'm working on, that's basically the list of strings that is the input for that puzzle. So that's where we start to look at my code. The same here as Sebastian did. We map this, split it, and map it to integers. So our histories, that is a multiple lines of histories, is a list of ints. I think we are the same on that entry point here. And the next thing is also the same. It's histories.sumOf, because that's what we want, right?
Mm-hmm. Yeah.
So the magic happens in the predict next. I think your function was very similar. It was just predict, I think, and you didn't use the extension away. I really love extension functions. That's what you see here. I always think of it like this.
Well, now, now that you say this, I'll go over here and I'll hit Alt Enter and I'll say convert parameter to receiver.
Yes.
And now mine also does it.predict. Okay, so we're closing.
Yes, we're getting closer.
You're already positively influencing my solution. Okay,
nice. So now let's have a look at how do we predict the next element in that history. So we have to look at this function here. The thing that I really love to use is sequences. So let's have a quick chat about sequences. When I read the puzzle description, I was immediately thinking of a sequence, because think of it. You have an arbitrary long list of numbers, and we know that we have to do something over and over again until a certain situation arrives. Namely, every value is 0 in our whatever layer. So this is a perfect example for a sequence. Sequences, they are just representing a sequence of things without having them in memory. They are basically a prescription of how to do it, or what comes next. They could be backed by some kind of memory stuff, but they could be just backed by an algorithm. Basically, this is where algorithms and data structures meet. That's where they have breakfast. Let's say it like that. So there is a cool function in the Kotlin standard library, just like many, many other cool functions. And this is called generate sequence. So basically, this is a very neat way in this situation. Generate sequence is a function where you basically say, I'm starting with a seed. That's always the start value of that sequence. So now this is something you have to, of course, first understand. Because this is an extension function, this here refers to the input list that we come from. So we generate a sequence where the first element is the list itself. So that's our first layer. And what comes next here, I mark it, this lambda function here is basically just the prescription on how to calculate the next layer given the current layer. So what the generate sequence function does is it gives you a sequence. That's the differences we get here. It's of type sequence of list of int. And here you can already see it is a sequence of lines, again, list of int. This is the line, the layer you called it, and it's now wrapped in a sequence. So we have an arbitrary long list sequence of these layers. And the lambda, let's have a look at this lambda. What is the prescription on how to come from the current layer to the next layer? So basically, here are some similarities again. You take the values v of that layer. I could call that layer or current layer. Oh, I don't have the permission to refactor. I can start the refactoring, but I can't press enter.
Oh my, okay, let me just...
I can't refactor my own code.
I must have changed something in the setup there. I do apologize.
It's not really important. We can stay with V here. Let's go back. Oh, is it done now? Okay, it's done.
Yes.
Cool. So, given the layer we have, how do we calculate the next layer? And there is one difference to your code. I really like this function zip with next. I actually didn't even think about windowed. So you took the windowed function, which is basically a way to take an arbitrary sized window, whereas zip with next is basically a window too. So that's the similarity. But I think it's more expressive because it really tells you I want each with each next value, just like the documentation says. I think you can see my hover overs, but it says 2 adjacent elements in this collection. Yeah, that's what it does. But it basically is the same thing as the windowed 2.
Yeah.
And here we have the same similarity, your code as my code. So we are taking the current layer, we are building the neighbors, we are building pairs of neighbors. And actually in this function, it already happens what we saw in the description. Zip with next reduces the list by 1 element because it basically bundles 2 elements together. So the resulting list is shorter by 1. And then we just take the resulting pairs, and what we do is we build the differences here. So b minus a, in this case, I like just to take a, b, and b minus a to visualize it's like the other way around. Take the second one and subtract the first one. Mm-hmm. And basically, if you take just the generate sequence call, this call here is all it takes to generate all of the layers without having them actually in memory, or even they are not even generated yet. It's just this is a way to get them if you need them. That's the cool thing about a sequence. It's lazily evaluated. It's there without ever doing anything unless you need it.
Well, I do have a question now.
Yes.
Because so generate sequence is awesome, but this if you were to like eagerly instantiate these, I suppose what the equivalent would be doing a reduce on your original list. A running reduce on your original list, where it would give you all the intermediate steps. But then this like whatever block you have would have to include the terminal condition as well. Like you'd have to. Okay.
Well, there's actually you caught me here. I'm just saying generate sequence is such a cool function. Actually, I'm not using it that often. And this morning when I started to do this, what I actually did is now don't scream, but I did a 0 to int max value dot running fold.
Okay.
So, the point was here, I didn't think of the generate sequence. So basically what you do is I'm using basically anything that drives my running fold. And I think I'm missing an S sequence here so that it actually compiles. So I'm taking a sequence of many values. I didn't care how many. It could have been max long value. Wouldn't be any difference. I'm making a sequence out of it. And then I'm doing a running fold with a seed, and here are the similarities. It's the same thing. The seed where the running fold starts is my list, and the prescription. Now, for the folding operation, you always have this accumulator, and the next. This is something I always start with ACCN because I know it's the accumulator first and then the next value.
Yeah. And
what you do in here, you basically do calculate the next layer. But then you realize quickly that you don't care about the driving iterator thing. The N isn't actually needed because each layer just depends on the previous layer. And when I was at this stage where I had the running fold with an arbitrary long driver, and then ignoring the index, I came to the conclusion I might as well use generate sequence, which is exactly the same as what it does.
Yeah. So a fun part here that Alexander mentions is that even with this approach, you could have used 0 until this size. You could have constrained it, but because you call a sequence on it, it doesn't really matter, because it's not like you're instantiating 2.1 billion integers and then iterating them. You really just generate the ones, you generate them on demand lazily, and then once your terminal condition hits, once you say I'm not doing anything else anymore, so you don't necessarily have to think about that.
And when I thought about it, I always come up with the indices.s sequence. That's just like the comment says. I could have used 0 to until this size, which is indices as sequence. Same thing. So if I had taken that, it would drive me for as many times as we have values in the first line, which is enough, because if you reduce the length by 1 in each layer, you don't need more than the number of elements you have in the first place, right? So this is enough. But then I thought, like, what does this tell to my reader? Where's the expressiveness? Because if I read this and I see indices, I think like my brain starts processing and like, oh, it should be important that we have the indices there, but it actually isn't. So, and that's when I said, like, what I really need is something like forever. Yeah. So, but you see, when you take int, you have at most the maximum number of integers. If you take long, you have at most the maximum long value. But generate sequence is actually the only one that actually does forever, because it doesn't. It's not bounded by any upper bound. Yeah. So let's fix this again. I don't know exactly what I have to go back to generate. Let's go back to where we started. Okay, Control Z or Command Z.
Okay.
So why does it? It just took a little bit. Okay. So as you just pointed out, the cool thing is that up to this point, we have an infinite amount of things. And if you think about it, if you do our prescription infinitely many times, we would end up very soon with 0 elements. That wouldn't make much sense. But it's actually not needed, because we have to look at this next part, which is very important. Whenever you create infinite sequences that, well, I knew that the thing I was looking for isn't infinite at all. I knew exactly when it should finish. And that's the cool thing. You basically start with describing what you need for arbitrary amount of times. And then you add at the end when you want to stop doing this. And the cool part is that even when doing the take while, so take while can be appended to any sequence. And it basically says, now take each element while this predicate is true. So you see here, it's like, as long as there is anything that is not 0, I will go on taking elements from the sequence.
Yep.
And actually, for those of you who understand and use sequences quite regularly, even up to this point, I didn't even call the function once. There is nothing that has yet run, even with doing the take while. So the take while is not really triggering the calculation yet. It's just generating a sequence.
Yep.
And then we come to the terminal operation.
Exactly. So you can look this up, and you'll see that first of all, generate sequence is lazy, of course, and then the take while chained operator is still intermediate, so it does not instantiate any values yet.
Correct. But just to stay with our task here, what I did then is I took the differences. Basically, I just refactored this so you have the name here. So differences is the layers from your solution. And what I do is I'm only interested in the last ones. And here it might be interesting to look at the puzzle again to see the triangles that we are having there. If you might switch to the browser window. So there is one thing that I did without even thinking about it. So if you look at this triangle on screen, so the prescription now says we start at the bottom with a 0, and we have to find the next number, which is just 2 plus 0 is 2. So that this triangle. And the next prescription is we have to take 6 and add whatever we had before, makes it 8. And then we have to take the next number and add whatever we have. And it doesn't take that much thinking that you see that basically the 68 is the sum of all of the last values. So it's 2 plus 6 plus 15 plus 45. Yeah. And that's actually already in my solution. Now you can go back to the solution. And all I do is here, given the last values of my histories, the predicted next number is the sum of them. And this actually is the terminal operation for the sequence, the one that triggers all of the calculations and basically sums all the values.
That's done. A very elegant approach, and there are no -1s anywhere here. That's kind of good. Very, very elegant. I do have to say, I think my favorite part about this is definitely, I really appreciate you also diving a little bit deeper into sequences and generate sequences here, because this is, I think, a pattern that, regardless of whether you do it in Advent of Code or somewhere else, is something that's quite useful to steal. This pattern of saying, hey, I'll generate an infinite sequence, and we will give a generic prescription of what should happen, and then as a separate operator, as required, I can stop execution or computation.
There are actually some cool videos on the Kotlin channel where somebody we all know describes all of this.
If you haven't seen those, I suppose you can go and check them out.
Yes,
might be a good time. We'll see here. We have a couple of comments. Simon says, I did my predict next as a recursive function. Not sure if that's clearer than a sequence. I was, to be fair, I was lusting for some recursion for the last couple of days. So it's yeah.
If you use recursion here, I mean, this is a clear case where you can have a tail rack recursion, and then it would be not that dangerous. Yeah. So I like to avoid recursion coming from that functional point of view, even though I know it's very much a part of some functional aspects. But I think it's helpful. But if you have something, when I think about this, and I think about an infinite sequence, something that might go on forever, I'm immediately not thinking about recursion anymore, because I know what happens if you do that with recursion.
Yes, true. But the nice thing really is that with tail rec, with that modifier, if you do that, it'll force you to rewrite your function in an end recursive format, and then at compile time will actually unroll it into a loop, so that there's no stack overflows happening anytime soon. Alexander also says, I think it is, and so we can express the next element in terms of the last element and the predicted for the difference array. Sorry, he said, oh, since we can express the next element. Okay. Okay. All right. And Ephemian says, even in a non-tail recursive form today, the recursion is bounded by the length of the input, which isn't that long, as we've seen prior. All so very good.
One might add that if you do this on part 1, my initial thoughts are always what might happen in part 2. So that's another point why I don't like to start with recursion, because then it might really hit you in part 2, because all of these prerequisites might be dropped.
Yeah. Now, here's a very interesting point that maybe we'll get to in just a little bit, because Alexander asks whether you can solve it in subquadratic time. But before we maybe talk about that, we can take a brief look at part 2, and then we'll head on over and see if there's some cleverness hidden somewhere here. So let's head on back over. Get ready. I'm gonna make sure the hat goes back on. It is still, I need to get this thing like headphone sized. Works fine though. We'll get right into part 2. Of course, it would be nice to have even more history included in your report. Surely it's safe to just extrapolate backwards as well, right? For each history, repeat the process of finding differences until the sequence of differences is entirely 0. Then, rather than adding a 0 to the end and filling in the next values of each previous sequence, you should instead add a 0 to the beginning of your sequence of zeros, then fill in the new first values for each previous sequence. In particular, here is what the third example history looks like when extrapolating back in time. Adding the new values on the left side of each sequence from bottom to top eventually reveals the new leftmost history value 5. Doing this for the remaining example data above results in previous values of -3 for the first history and 0 for the second history. Adding all three new values together produces 2. Analyze your OASIS report again, this time extrapolating the previous value for each history. What is the sum of these extrapolated values? Olaf, initial thoughts.
I was like, wow, nothing breaks my neck now.
It's like you were already seeing the free weekend ahead of you.
Yes,
like...
yes, really. Because if you read it, you know, okay, now you have to do some other logic, but there is nothing that like opens the solution space to a very, very large space where anything could break. So that was the thing that really made me feel safe even when reading it. Of course, you have to do some thinking of how to calculate now. And that's something that I was initially fighting with a little bit. Because there is only one difference I saw immediately, and that is what we just discussed, that for the end values, you basically sum up the last values to find the next one. And here, as you go through this algorithm description, you see it's not the sum of the first values. Yeah, that's not what it is, what we're looking for.
Yeah. So the way I approached this was twofold. Let me just open this up on my end here. The nice way of doing it is, of course, realizing that you can take each individual line, and no, it's because we did a little bit of a refactoring here, is that you can take each individual line and then just reverse each of those lines. Essentially,
that's a very cool one.
Yes, and this is again the classic story that we've already seen a couple of times. Sometimes you can just transform the input in a way where you express the second part problem in terms of the first part problem, so you don't need to adjust.
Did you do this morning immediately?
I didn't do it this morning immediately. I will be very honest with you. What I did this morning immediately was I took the same code and I squinted very hard and made sure that I switched out all the lasts for firsts where important, and I made sure that I switched the our operators from left plus below to right minus below, which again, prior to a first coffee, I think we had someone else also mention, I think it was Rob, perhaps? Oh, no, it was, I think, Jonathan. Yeah, it's easy to mess up when there is a negative number somewhere. So having a plus or a minus somewhere can be tricky. But then, like, after I wrote this, or essentially halfway through me writing this, it's like, wait a second. Like, really, we can just transform the problem. And we can just turn it around, and then the whole thing just condenses into a single line, which is nice.
And that's very elegant, and I must say, we have something prepared here, or I have something prepared that explains why this is absolutely correct, what Seb does here. Absolutely brilliant. And my optimized solution that I wanted to show you is like fading now, because it's like, okay, I can show you a little bit more about sequences, but this is brilliant, and why it works we can have at the end as a little discussion. Why it must work.
Oh, very good. Yeah. Rob also mentioned that, yeah, you can do just like reverse with predict next And I think we've had some other folks mention prior, yeah, like just adding reverse to the part 1 solution works just fine. Awesome.
I'm pretty sure that this is the reason why the really competitive programmers, those who do this like in very few minutes or even seconds in the days 1, 2, 3 or whatever, because they have exactly this feeling immediately. Where I guess me, I'm just copying my part 1 solution and adopting it and letting it run again, and I'm fixing the minuses and pluses. And I think if you do this as a competitive programmer, this is what you know immediately to do. Yeah.
But I think we can still see what your solution for part 2 looks like. So we're back in your project, and I'm gonna follow you again.
So really, this here stays the same, definitely. So you sum up, and now it's only the different function predict previous. And to be honest with you, this code here, of course, doesn't look that clean at 6 in the morning. So even the function names, this is something I do after the fact. I don't type this in the morning. And this is also something that breaks my neck many times because I'm using 1-letter variable names and stuff like that. Horrible. Yeah, but okay, let's focus on what we have to change now. And if you compare the 2 methods right next to each other here, next and previous, so the differences are exactly the same. It's just because I copy and paste my solutions and do quick adoptions. And so clearly, this one here requires us to only look at the first values.
Sorry, give me just 2 seconds here.
Yeah.
So the difference starts here. We're looking at the first values. And now, as I said, the problem is, if now you can switch back to the triangle on the Advent of Code page, the difference now is that you can't just sum up these first values. So it's not 10 plus 3 plus 0 plus 2, as we had in the part 1. The prescription now really goes, if you start at the bottom, the value you're looking for is the value 2, the first value of the last line, minus the 0. So you do the 2 minus the 0. Yes, that 2 minus the 0 beneath it to get to the first 2. To get to the minus 2, you start with the 0 on top of the 2 and subtract the 2, the new value we just found. No, the other 2.
Sorry, this one, sorry.
Yes.
Yep.
So we come 0 minus 2 is minus 2. And now we have to get to the 5. The 5 is the 3 minus our previous value minus 2, and that makes it a plus 2. So we come up with 5. So, and because I was really tired and I was seeing that I could grasp the solution very quickly, I just did that. And if you go back to my code, the problem you now encounter is I have to go to do that exactly like that in the morning. You have to go from bottom to top. So I have the first values, but it's a sequence of integers. And here we come to the things that you cannot do with a sequence. In order to go in reverse in a sequence, we first have to materialize it. You see here, to list reversed is basically taking the first values, transforming it into a list just to be able to reverse it. The reason is very, very simple. Because the sequence is just something we don't know what's inside. It can just produce the next value. And it could be infinitely long. You cannot reverse it. You have to use memory to reverse a sequence. Okay, another way to do that would be to rewrite the sequence like with an algorithm. You could do that, but you can't look inside a sequence that you just get. So there is no way to do dot reversed on a sequence. So going first values to list reversed, we are going through the first values in reverse order. And here you see the folding operation for the first time. Starting with our initial value 0, that's the lower 0 in the new line we added in the new layer. And the folding operation now has this accumulator and the next value. And it does exactly the subtraction we just discussed on the graphical side, like taking the next value and subtracting what we already have calculated. That's the direct approach to this algorithm, and it just delivers the first value on the top layer.
That makes sense. It works around the small limitation that you've had with your sequence. But apart from that, it's a pretty straightforward approach.
Yeah.
And it only works, of course, because we are dealing with very low numbers there. So if the sequence is like millions of elements, that would be really costly.
Yeah, because you would have to,
works.
of course, instantiate everything and keep all of that in memory. Simon says, of course, and this is perfectly valid. Reduce write with int minus. That also works.
And of course, reduce write also requires this to be a list. You even without looking at the code, there could be no sequence dot reduce write. I think it doesn't exist. It cannot exist, because to do that you need the thing in reverse.
Yeah.
Okay, cool. That's basically what I did this morning, just a little bit beautified so that you can read it. Very straightforward, I would say. Yeah. That's basically it. And the thing that, because I didn't come up with your brilliant solution to just reverse the input, what I was thinking a lot about is like, why is it that part 1 can be done without allocation? Because we just do the sum of a sequence. It basically runs without, of course, we have allocations. Each layer is a list, definitely. But to come to the result, we just sum up the sequence of integers. And why is it that this, well, if I look at this code, I feel the symmetry is broken. Why does this algorithm require me to now go for a list to do it reversed? And that was my attention. I wanted to have this just like the sum. I wanted to have it without reversing the list. And so what I did is I basically had a look at the triangle. I think you're not following me. I just switched to the optimized one.
Sure, here we go.
Yes. So the only thing I wanted to solve is now, how can I get to the number 5 up on top here without reversing my first values? So that was the task. And what I did is then I just gave these first values names. So I just said, this is A, this is B, this is C, this is D. And then I just put in the math here. So the 2 here is actually the D minus the 0. So this here is D. So what is the -2? The -2 is the C minus the D. So this here is C minus D. And going on like that, you find that the 5 is the B minus, and now the C minus D comes here. So it basically takes this value and subtracts this value. And if you just get rid of the parentheses, you come up with this solution. And the topmost value we are looking for is basically A minus the B minus C plus D. And if you get rid of the parentheses, you have a plus and a minus here again. So basically, this is what I came up with. This is the value I'm looking for.
You got this one, I think.
So,
there we go.
Yes, sorry. So basically, you see, if you do this one here, and you see it's alternating in signs. So it takes the first value and then minus, plus, minus. And if you do it with the other examples, you soon find out that this is the pattern. It's minus, plus, minus, plus, minus, plus. And having that, the previous here, this is the function with a little bit nicer approach. You take the first values. I don't need to take the list and reverse it. What I do is I say alternate sign. And now you might wonder, what is that? Of course, it's my own extension function. It's an extension function written on a sequence of integers. And it brings you another integer sequence with alternating signs. That's what it does. And then you can do the sum of it again. That's the magic here. But it's all really fading against just reversing the input. I can't get that out of my head.
But I do like this approach because it does make a little bit more use of I suppose the structure of the input or the properties in a way.
You can play around with sequences and such. So Advent of course is always something to learn.
And of course your alternate sign approach here is also lazy, or it's also an intermediate operator.
Yes.
So it doesn't do anything on its own. So that symmetry or that laziness that you were wanting for is indeed returned.
Correct. That was my aim here.
Yeah, but I'm not sure. I don't think this really addresses the previously mentioned optimization question, or maybe there is even more optimization to be had here.
Well, there is much more behind this. And this is, so what I do usually with Advent of Code is once I'm done with the puzzle, once I've cleaned up my code and I'm satisfied with solutions like you've seen here. So this is something that makes me happy in the morning. Like this is, let's say 9 o'clock. So coming from 6 o'clock here in Germany, this is 9 o'clock when I do these kinds of things. And after that, maybe at lunchtime or something, especially on the weekend when I have more time for this, I always hop over to Reddit and see what other people have found out what is behind it. And so actually what we find here is a pretty cool mathematical thing. And I'm pretty sure that some of our viewers have already seen that or knew it from the beginning. I'm interested. Did anybody know that what the mathematical background of all of this is here? What are we doing? Shall we just hop over to give some hints?
Sure. Where would you like me to hop?
Yeah, I'm hopping to my math one here, just because I have some insights here. So basically, what I did when Googling around and reading through what people did, you soon find out that this is actually something very cool. It's a math thing we're doing here. If you think about it, this is a sequence of numbers, and we are asked to. So you know these IQ tests, basically. They give you a number list and they say, what's the next number? Yeah. And you wrap your brain around it. And what is this number? And why is it this number? And if you have time and if you're interested in that, the Mathologer is a cool channel on YouTube doing math stuff. And he has a complete video that takes 40 minutes. And it's exactly our Advent of Code problem explained in very detail. Now, I'm not a mathematician, so I won't try to even go deep into that. So I'm really saying go to that video, and you got it open in one of your tabs. So basically, you can show how it looks. And you might see the similarities here. It's exactly our AOC problem. And you see, it starts with the top line. That's the sequence of mystery numbers, what he calls them. And the question is, what comes next after the 163? And if you watch the video, he basically explains in much detail what this actually is. And what we are dealing with here is discrete differentiation. So if you remember your math time and you do some calculus, we are deriving functions here. And the difference to what you may have learned in school is basically we are having discrete values here. So our list of mystery numbers up here, if you think about this as the points on a function. So the leftmost is at position 0, it's value 1. At position 1, it's value 2. At position 4, it's value 4, and so on. And just think about this on a graph.
At position 3, it would be value 4, yes?
0, it starts with 0, so 0, 2, 0, 1, 2. So the 4 would be at the 2. Yeah.
Gotcha. Okay.
So if you think about it, the question is, what kind of a graph can you put through all of these points in order to come to the next value? Yeah. Of course, somebody made a video of this, but he didn't do it about the Advent of Code. This is 2 years old, and the math behind this is even older. So long story short, if you go to the next screenshot that I just sent you before that. So basically, the math behind it is, what is the polynomial? So the function f of x behind these given numbers that matches exactly these points. So tell me what is the function that goes through these points that I was given. And the math behind it tells you in the end, down here, you see this is the equation. For any kind of n, so n is the index. So for the 1, it's 0. Yeah. So given any n, this formula here, down here, basically expresses the function we are looking for. If you're not familiar with the parentheses, it's called n choose 0 and n choose 1, n choose 2. It's combinatorics. How many possibilities are there to choose 0 values out of n values? So you don't have to understand all of that, but basically this is a mathematical thing. You can find libraries for that or write it on your own. And if you plug in the first values, 1, 7, 2, 8, 2, exactly the ones that we are dealing with in my differences.first, you immediately have the formula. And now you can basically plug in any n and calculate exactly the value for n. And our AOC question basically was, what is the value for n equals size? Yeah, so last index plus 1. That was the question in part 1. And the question in part 2 is, what is the value for -1? If you plug in -1 into n, you will immediately get the first value that we were looking for in part 1. And you can see my code if you hop back on my code. So what I did, because I love Kotlin so much, I put this knowledge into exactly this little function here. So this function is an extension function, again, on list of integers. So given an arbitrary list of integers, this is our numbers, the history we have. Please generate the function f. And you see the return value of my generate f is a functional type. It's a function that takes an int. My keyboard doesn't do the undo. I double-clicked and moved it. Maybe you can do the undo. Oh no, you see it differently than I do. Okay, there's a difference in the screens. Sorry, it's just a difference in what I see and you see. Basically, you see here, the firsts is my difference sequence. I can't hop there anymore. Something is broken here, Seb.
we can try closing and reopening this this window on my host for a second.
Maybe you just mark what I wanted to explain. It's very easy to do.
Yes.
So the firsts are the different sequences and taking the first values. We've had this before. And all I do is with index, I need the index because the math function we saw, it needs the index because we have this n choose 0, choose 1, choose 2 with each position. So I'm adding the index to that first value. And the function I return in lines 49 to 51, that's the function I create. This is the formula you just saw in the video. It's the sum of c, that's the coefficient, times, and comp is the function, this n over index. That's exactly what we had in the video on screen before. Yeah. And
very
the cool
interesting.
Thing is,
this is not part of the standard library. That much I know.
Yes, yeah. That's basically just the algorithm to do the math behind it. And we had this question before, if we can do it in a faster way, right? Like not quadratic. That's what was asked before. The problem is, I wouldn't necessarily say that this is much faster because calculating this value is efficient, but it requires some calculations. Of course, you can do some caching and cleverness here, but you can't get away with reading every value in your list, of course. That's the math of it. Every value has to be in it and has to be computed inside this formula. Yeah. And the cool thing is, if you scroll up again now, our questions here, so next and previous, I should have called them predict next and predict previous. These are our questions in part 1 and part 2. And what I do here is I show exactly how I use my function. I say, please give me the function f I'm looking for, generate the f. And then my first thing is just give me the f of last index plus 1. So the one following the last index. It's like looking into the future by accessing the last index plus 1, which you would never do on the list, of course. No such element exception. Yeah. And for the previous, you basically say, okay, give me the function and then give me the -1th value of that function. And it works.
That's pretty
I did a test. Yeah, I did a test up front here in lines 21. I wanted to know whether it really is my function, because now if I have a function f generated by my input numbers, what must be true is if I iterate over any of my given numbers and ask the function f of index, calculate the value at that point, it must be the expected value. And this turns out to work. It's like a unit test.
Yeah, this is really elegant. So quite literally with this you do kind of reverse engineer like what is the actual function. And I suppose with this, if the problem had asked you to predict 20 more numbers to the right or to the left,
yes,
you would,
easy.
Yes, exactly. This would have just continued the same path. Alexander does mention, and I think this is what you did address, because you still need to do a bunch of computations. It might still be an n-squared solution.
Yeah, the program has to materialize the layers. Correct.
Yeah.
Yeah.
And I think there is some folks who've also mentioned that you don't need to keep all the lists, and that there is a different approach. I can pull this up on screen, but I doubt that having this in just the overlay functionality is particularly useful. So if you are interested in finding a more efficient solution, I'd encourage you to maybe either stop by our Kotlin Lang Slack or also potentially find the Reddit. But I have to say, it is very clever.
There's always ways if you really want to optimize stuff. Like if you do it the way I like to do it, of course you are generating objects. Like even if you do a sequence with lists inside, you are generating these lists. And those who come from non-functional and C functional, they're almost always the first fear isn't that very slow, because I avoid mutability, I create objects. And the short answer is, yes, we create objects, but no, it shouldn't be of an issue. Because nowadays things are that fast, and creating small objects is really, really efficient. And it turns out that except you have a really, really hard computational problem, you shouldn't spend time on optimizing it in that way. So if I wanted to avoid this, I could use one mutable list and reuse the values. Yeah, very good. That's a good article to pull up there.
Yes, I figured that, and I'll also happily link this in the chat over here if you have not read Roman's post on this, which I think makes a bunch of the arguments the same way that Olaf does.
Yeah.
And I personally, I agree with you that having it's always about optimizing for your domain as well. If you're planning on writing an algorithm that's supposed to run on a e-paper display running on a single cell battery, maybe this is not the correct approach. But given the problem, and given the inputs we've had, it seems like a wonderfully elegant solution, and it does exploit the math behind it in a quite interesting way. Femian does say they do have a more efficient solution, which they've left in the Slack. So if you are curious, then this is a great time to once again remind you that we do have a community of wonderful and very actively chatting people in our Kotlin Lang Slack. So if you haven't joined that yet, make sure you head over to the Advent of Code 2023 blog post with Kotlin, and you will be able to join right from there. And of course, the typical other points apply. We have leaderboards with a new one so that there's still space for you to join. There are prizes, and there are a couple of things that you need to do in order to get those prizes. So that's just a quick side mention here again. Yes. Simon also mentioned that, yes, it's also n-squared. The evaluation of f is n-squared, which I suppose sounds about right.
Definitely, yes.
And Alexander also mentions that you can also create a sequence generator that generates the sequence of all binomials, modulo 232 or 264, depending on int or long, I suppose.
And if you do that, you would cut down the calculation time, because that's the thing that, correct. If you dive into the functions, you'll see why that is. Like the combinations calculation, it includes factorials, and it can be made more efficient. Yeah.
So this is if we go into our comp here.
Yeah, and this is already it's not the one that uses the factorials. It's an efficient algorithm. But if you do that for every coefficient in our function, so the longer the list of numbers, maybe we can dive into that a little bit. The polynomial we are looking for, the degree, like if you come from the math background again, do we have a line or do we have a parabola or a cubed function? The degree depends on the number of given history values. Yeah. So the more we have, the deeper our layers go, the higher the degree of the polynomial. And the higher the degree, the more of these coefficients we need to calculate. And if you cache them and if you don't do it over and over again, which I do here in the naive approach, you can get faster, definitely. Yeah.
And of course,
and there's also another cool thing that I found just before we started our chat today is if you look at line 11 here, this is so cool. It amazes me every time I go through these kinds of things again. If you look really closely, what you see here is we are alternating signs. So if the n is negative, we have to do, if k is an even number, we take 1, otherwise we take -1. Now think about my solution for part 2, where I did the alternate signs sequence. And here you see how the things fit together. It amazes me so much because you can't get away with this without understanding the math. Yeah, so it's amazing, isn't it? So this is the part that made me do the alternate signs without knowing what I'm doing. Because if you look at the polynomial, if you calculate n over k and n is negative, you have to do this. Yeah, and this is exactly what you do even if you don't understand what you're doing.
Yeah, that is a very fun, like that's a great story arc right there. It really is, like it all fits back together from the first alternate sign to just rediscovering. I suppose it really is just it's patterns all the way down.
Yeah.
Yes. Rebbe also mentions that alternatively you could also do -1 to the power of k, which would also work. I think power is
it's only on doubles.
Yes, they're only on the floating point types, so we don't have a super nice approach for that here. It will just involve a bunch of casting.
Yeah.
Yeah. Wow. Well, I really, again, when I started out in the morning, so I was like, well, it's going to be a cute little quick discussion about how we alternate like a sign to add something to the front, and apart from that, just sign something at the back. And I have come out of this having learned something new, like 100%. I am very excited. It's very exciting that you also did share this mathology video, and I will also put this one in the chat for anyone who would like to dive into this a little bit after we wrap up here, because it's very much worth it. Yeah, man, it's always like this. Honestly, I would have to say personally, these are my favorite types of puzzles because they allow you, if you would like to just solve the puzzle, they don't, as you put it so nicely, they don't break your neck in the morning, but they invite you to see if there is a nicer way to do it, if there is a better way to approach it, and then you can go completely crazy with optimizations, or with polishing your code and seeing what you can do. So I think it has this also makes it very appealing both for beginners and for people who want to dive really deep into the topic, which is always great. Yeah. So I think we've already heard it a little bit from you earlier, but I am curious. Do you have any predictions for the upcoming days?
Oh, yes.
Yeah.
I have a prediction, which is also a wish of mine, of course. So I really want to see the first maze puzzle for this year. So something where we have to escape a maze, find something. I recall some very, very cool puzzles. I don't say that because of the possibility to do some visualizations there. I also really enjoy these kinds of puzzles. And do you remember last year when we had to do the cube? I mean, this is going to happen further along the road, but those are the puzzles that are really so wonderful to solve if you can spend time with it and come to a solution. Wonderful. So tomorrow it's gonna be a maze.
Okay, that's a great prediction.
I don't know. I have no idea.
Well, no, we'll work with that. And I suppose the best way to, of course, find that out is to do those puzzles tomorrow. And of course, to check back in for our Sunday stream that will happen at exactly the same time as this one, where I suppose we'll see if the prediction comes true.
Don't blame me if it doesn't.
Yeah, I think no, I think that's perfectly fine. Yes, so we'll see how it goes, and I'm sure you'll get your mazes and graphs eventually, soon enough. I'm sure. Well, with that, Olaf, thank you so much for joining today. It was really lovely to have you.
It was a pleasure to be here again. Thank you very much.
And it was an absolute delight. So yeah, I hope that we get to see all of you who've decided to join today in some of our upcoming streams as well. We will be streaming again tomorrow, as well as on Monday and on Tuesday. So make sure you tune in, because like every time, we do have other guests coming on who will provide another unique view, a unique perspective on the advent of code puzzles and potentially on Kotlin itself. So yeah, make sure you tune in then. Maybe spend a little bit of time puzzling yourself, and make sure you let us know how it goes afterwards. Awesome. Great. Then all I can say is enjoy your Saturday, and hope that you'll tune in again soon. Take care, everybody. Bye-bye.
See you.